All right, good morning, everyone. We're going over Earth's greenhouse effect today for Lab 9. This ties into last lab when we were talking about the different molecules in the air. So 99% of it is oxygen and nitrogen, but there's that 1% that has a pretty big effect on the amount of heat that's trapped within our atmosphere, and that ties into our Earth's greenhouse effect. So if we're going to go specifically into it, we're going to have to compare weather versus climate. Weather is, if you don't like it, it's going to change in 5 minutes. But climate is more location based. So if you don't like the climate, you might have to move. What this means is that location, weather, it's very temporary, minute by minute, within like the day, very next day, it changes very quickly. But climate, we know, is more predictable. So that if you don't like the climate in a certain area, you're just going to have to move to somewhere else. So climate is very place location based. So it depends on where you live, the latitude, how far away from the poles you are, your altitude, how high up in the mountains or close to the valley you are, and what's upwind. Are you near the ocean or land? Is there warm ocean currents blowing in? And that can also change your climate for that area. We know that climate, it generally changes very slowly, so it's very predictable. And that same way that we can predict that Phoenix is going to be warmer than Fargo is precisely the same reason that we can predict a warmer future. So there's a lot of data that goes into predicting the weather and looking at trends like CO2 carbon dioxide trends. So we can pretty accurately predict that the climate right now that we have, it's making these changes that haven't been seen before. But have we ever wondered why day is warmer than night? Summers are usually warmer than winter, and Phoenix is warmer than Fargo. We can actually attribute that to heat budgets. So the amount of heat that goes in minus the amount of heat that leaves is our change in heat. So if we're thinking about summer days, we have longer days in the summer, so there's more heat going in and less heat going out. So our change in heat is going to be higher than during the winter time, where our days are shorter. There's less heat coming in throughout the day. That means there's less heat leaving, so the change in heat is going to be lower. So we can attribute that to, if we're thinking specifically about electromagnetic spectrum, where the different types of energy or different types of light that we see in the visible wavelength um, has different wavelength and different energies. So as it increases in wavelength, it also increases in heat. So but also decreases in energy. And that's something that we can kind of tie into heat if we're thinking about it on the electromagnetic spectrum. But now if we're going to go into the greenhouse effect, what does that mean for Earth as it starts to heat up? Well, we know that we have our Earth here, we have our atmosphere over our Earth, and our sun. So our sun shines in and shines in light and heat. Around half of it is reflected off of the atmosphere. Another half of it is absorbed in our oceans, in our Earth, and some of it would try to escape and bounce right off of our Earth, either bouncing off of any light surfaces like clouds or ice or anything like that. But some of it is trapped within the Earth by infrared radiation from the surface. It traps in this like light that comes in from the sun, and some of it's scattered back and forth. Other things that trap in heat really well is greenhouse gases, where we're going to go specifically into why, but the more greenhouse gases we have here, the better they are at bouncing around and keeping heat and light within our atmosphere. So that's the greenhouse effect. It's based on the idea of a greenhouse where you grow plants within it and it just traps in heat really well. So that is the version in our atmosphere of a greenhouse effect. So if we're thinking about more why certain molecules hold in heat really well, well, 99% of our the air is in the air that we breathe. 99% of it is oxygen and nitrogen, and they have a diatomic. They're diatomic molecules. They have this type of structure where it's the ends are identical. So we have our oxygen connected by our two bonds, our nitrogen and their bonds, and these atoms are the same elements, so our O2, N2, and their infrared heat energy can be absorbed, but it's not done really well because of the structure that they have. They don't hold in heat really well. But if we're thinking about greenhouse gases, say carbon dioxide, water vapor, CH4. So even water vapor is a form of greenhouse gas that holds in heat really well because these ends and the structures that they have more, they're more flexible and they can wiggle around more. They hold in heat really well, and there's just more ways for these structures, these molecule structures to vibrate. So it's not that it's not that like one CO2 is bad because it is. It's unfortunately just that their structure of CO2 holds in and traps in heat really well, and other versions of greenhouse gases do that too. And this idea, the absorption spectrum of CO2, was measured by John Tyndall in 1863. So now if we think more about it, we know that if we double our CO2 concentration, it's like adding a Christmas tree light to every square meter across the earth. And at first this doesn't sound like it's a lot, but if we have that one Christmas tree light on all the time in every square meter for 24 hours a day, 7 days a week, 365 days a year, we know that things would start heating up pretty fast. And so that's what it would be like if we were to double the CO2 concentration. Our Earth would start to heat up pretty quickly. And doing that would make the surface warmer. This is introduced by Svante Arrhenius in 1896. And it's nice to give credit where credit is due. So this is the person that came up with this idea. So one common myth is that people are worried about climate change because it's getting warmer lately. And that is generally true. If we look at data, this is collected from the Mauna Loa Observatory, where over time, we can see that heat and the difference in degrees Celsius, it is increasing over time. So generally it is getting warmer, but along with getting warmer, more specifically, we know that if a system holds in heat, or if we add heat to a system, it's going to get warmer. And that's if we're thinking about the greenhouse gas effect. If we add heat or light into the system, our greenhouse gases would not only make things warmer, but traps in that heat really well and just kind of exacerbates that. So we're concerned because energy, when we add it to things, they're going to warm up. And all of this data to look and predict and let us know that climate change is happening and the things and our Earth is warming up can be seen through different ways of collecting CO2 data. So one of the ways to collect these changes in CO2 is through ice core samples. And so for the past 420,000 years, these from ice core samples, we can see that there are changes in CO2 over time, and it varies mostly, but they're mostly in between 180 to 280 ppms. And we see that at various cycles, there actually is this dip where we're supposed to have an ice age, an annual ice age, and actually we should be going through a cooling cycle right now too. But from more recent data, we know that we have certain ranges in time we're supposed to go through an ice age and a cooling period. But after the Industrial Revolution, the CO2 concentrations have dramatically increased and have passed 400 ppms in 2016. And this data is also taken from the Mauna Loa Observatory in Hawaii, where the Mauna Loa Observatory is up on a mountain where there's very little light pollution, air pollution from surrounding land or anything like that. So we can see that CO2 concentrations, it's getting quite high over time. And this, the amount of CO2 and different greenhouse gases have mostly been added into our atmosphere from human impacts. And one of those is through carbon dioxide via fossil fuel burning. So, industrial power generation is responsible for around 25% of global greenhouse gas emissions. So, industrial power generation, as in generating energy through fossil fuel burning, coal burning, but other ways that we contribute CO2 is through driving our cars, or if your home doesn't have solar or wind energy, it's most likely powered through fossil fuel burning. But I think one nice thing to keep in mind is that we're actually, coal is a very finite resource. You can't use coal forever. If anything, we're realizing that more now. So there is a dramatic shift away from coal to solar and wind energy. So that's one nice thing to know about fossil fuel burning. It's still an issue at the moment, but we're making that transition to more renewable energy in general throughout all of the countries. So I think that's one nice thing to remember. But another human impact is through our livestock consumption. So CH4 or methane that's produced from cow farts. So agriculture and land use are responsible for around 20% of global greenhouse gas emissions. And because we like to eat meat so much, there's around 1 billion cows in the world, and each cow makes around 100 kilograms of CH4 or methane a year. So that's 100 billion kilograms of methane produced in a year. And yeah, and other ways that methane can be introduced into our atmosphere is through landfills. If you don't separate and your trash, like via composting, trash, recycling, and such, your food waste that's in landfills, when you don't properly sort them out, they can well, overall create methane if they don't go through the decomposition process in the right way. Landfills produce methane along with different things like livestock. So one thing to know about CO2 versus CH4, so carbon dioxide versus methane, is that carbon dioxide, it it has a lower, it doesn't trap in heat as well as methane, but they have a longer, carbon dioxide has a longer lifespan. So even though it does trap in heat, but not as well as other greenhouse gases, because it lives so long, it's a very, it's something that we have to worry about reducing. And CH4 methane, it doesn't have as long of a lifespan as carbon dioxide, but it holds in heat really well. So that means that over time, we, even though it has a shorter lifespan, it makes a pretty big impact that's almost comparable to carbon dioxide. So that's something to remember about that. Now we can go over the Lab 9 exercise where we're going to create CO2. There's a couple of different ways that we can create CO2, either through dry ice or adding vinegar and I think some other compounds as well. But yeah, CO2 doesn't have to be created only through driving your car. We're going to trap it in a container to simulate human impacted atmosphere. So we're going to have one container with our no CO2, just regular air, and then one container where we're going to make CO2, put it in, and then shine a light on both of them to see the differences in heat over time if we shine a light source on it. And we're going to compare those temperature changes and then make a graph. But all of that data will be given to you. So first, if I go, you can find these videos in our lab videos in the Lab 9 Canvas page. So let me just share that screen. And if we're in the Lab 9 Canvas page, you can scroll down. We have our background information here. And these are our 3 videos. This is a 2-minute video basically talking more about the molecular structure and how different greenhouse gases hold in heat really well. If you want a more in-depth version of explaining why greenhouse gases like hold in heat really well over time, and there's this 8-minute version of this video that you can watch in your own time. And then this is the lab demonstration video that we're going to watch together. But first we can watch this video and go over the information here.
The Earth and the Moon are basically the same distance from the Sun, yet temperatures on the Moon average an unlivable -18 degrees Celsius, and even deadlier, they range from -170 Celsius during lunar night to 100 Celsius.
Maggie, when you mute yourself, we can't hear the video.
Shoots. All right. Let me try that again. I thought I like actually shared my here. Let me try my new share. Okay. I can see why. I get it. Let me know if you can hear it now.
The Earth and the Moon are basically the same distance from the Sun, yet temperatures on the Moon average an unlivable -18 degrees Celsius, and even deadlier, they range from -170 Celsius during lunar night to 100 Celsius at lunar noon, regularly exceeding both the coldest and hottest temperatures ever recorded on Earth. And while the days and nights on the Moon are about 14 times longer than those on Earth, our planet's relatively fast rotation isn't what spares us from those loony temperatures. What protects us is our atmosphere. By day, it serves as a shield, blocking out the most harmful and energetic of the sun's rays and about 1/3 of the less intense but visible light. At the same time, it traps the infrared radiation, aka heat, radiating out from Earth's sun-warmed surface, keeping us from freezing solid at night. In order for our atmosphere to absorb any kind of radiation, it needs to have some electrically charged particles for passing electromagnetic waves to push around. And most of our atmosphere is made up of gas molecules that don't have an electric charge. They all have a balanced number of positive protons and negative electrons. But some molecules hold most of their negatively charged electrons closer to one side, lending them a lopsidedness that can jiggle back and forth to absorb the energy of incoming infrared rays. For example, water, ozone, and nitrous oxide are all electrically lopsided, so they all absorb infrared radiation. Then there are gases like carbon dioxide and methane. On paper, neither molecule looks lopsided, so it doesn't seem like they should be able to absorb any radiating heat. But in reality, gas molecules aren't motionless. They crash into each other billions of times per second, knocking each other in different directions and also into different modes of rotation and vibration. And it turns out that both carbon dioxide and methane spend most of their time shaking it in electrically lopsided ways, allowing them to absorb infrared rays and help insulate the Earth. Even though many different kinds of molecules can absorb infrared radiation, the vast majority of our atmosphere can't, because it's made of nitrogen and oxygen, which don't get lopsided even when they are vibrating. They're too symmetric. Nevertheless, the lopsided 1% are such good infrared absorbers that they manage to intercept about 90% of Earth's outgoing heat. Each captured ray gets pinged around the atmosphere, and most end up returning to the surface at least once before escaping to space. We don't need to visit the moon during frigid lunar night to know just how important the game of radiation pinball is for Earth. Ice records from our own coldest climate show that small natural variations in atmospheric carbon dioxide produce relatively big changes in temperature. They also show that, compared to the last 800,000 years, the game today is much, much harder. Thanks so much to the great team over at Kurzgesagt for doing the animations in this video. It's been a lot of fun work.
So that was a really good video to give a brief overview on how we were talking about the different molecular structures of greenhouse gases and how they hold in heat while within our atmosphere and creates the greenhouse gas effect. Now, if we're going to look at the lab demonstration video, our lab manager, Darren, is going over how to make CO2 and look at the changes in heat over time. And I will play that for you all now. It's like a 5-minute video, and I'll talk you through the changes when we see the temperatures. Like go.
In this video, we will be doing a walkthrough of the experimental portion of the ENVS 100 lab on the greenhouse effect. Our setup consists of 2 flasks with rubber stoppers in each, as well as 2 digital temperature probes, a desk lamp with a 60-watt light bulb, a little bit of water in each flask, and finally, a little bit of dry ice. One of our flasks will serve as a control environment, representing the Earth's natural greenhouse effect. The other flask will represent a greenhouse effect that has been amplified by an increase in concentration of greenhouse gases, in this case, CO2. The rubber stoppers will allow us to seal our environments, making them closed systems. The temperature probes will slot through a hole in the top of each stopper and allow us to collect data from inside of our environments. The lamp will represent the sun, giving off visible energy in the form of light, as well as infrared energy in the form of heat. The small amount of water in each flask will represent the oceans, and the dry ice will provide us with an increased concentration of greenhouse gases in our experimental flask. To summarize, starting from room temperature, we will be observing the differences in temperature between a natural greenhouse effect and a CO2-enhanced greenhouse effect when exposed to infrared energy over the course of 15 minutes. Temperature data in degrees Celsius will be collected every 30 seconds for 15 minutes. There are 2 important things to note in regards to our use of dry ice. One is that while we often think of gases or air as having weight, CO2 gas is actually heavier than the air we breathe, which is mainly composed of oxygen, O2, and nitrogen, N2. Here, I've added our dry ice, our CO2, into our flask, and as you can see, this little foggy area right here is sitting quite low in the flask. This is all of the solid carbon dioxide returning to its gaseous phase. As it sits low, and as it's heavier than air, it pushes air up and out of the flask. This allows us to assume that we have collected a fair amount of CO2 in our flask as we run our experiment. The other thing to note is that CO2 in the solid phase as dry ice is only possible due to extremely cold temperatures, hence the name dry ice. That means, as you'd likely guess, when we add dry ice to our flask, it will lower the temperature of the flask significantly. To maintain our experimental design, we will wait for the CO2-enhanced flask to return to room temperature before we begin collecting data. Okay, so it's been a few minutes, and the CO2-enhanced flask has returned to room temperature. Both flasks are sitting at just about 22.9 degrees Celsius. So once again, our data probes are set to take a temperature reading once every 30 seconds, and we will begin running our experiment over the course of 15 minutes.
So our control flask is this lower blue line, and our CO2 enhanced flask with the dry ice is this line on the top. We can already see that there's like a change or difference in their temperature from the CO2 flask and our control flask.
And that's our 15 minutes of data collection. The data will be exported as an MS Excel file and posted on the lab Canvas page. You will be using this data to create graphs and answer questions as assigned by your lab instructor. This concludes the ENVS 100 greenhouse effect demonstration. Thanks for watching.
Right, so that was our looking at the two different flasks, one with CO2, one without, and the data that Darren was talking about is available right underneath that video. So there's the Lab 9 assignments and the questions and assignments and the Lab 9 data. We are going to click and download this Lab 9 data and it will open an Excel sheet for us. So this, if you click on the black arrow button right next to it, it would download it for you all. But once you've opened that, it would look like this. Our Excel sheet would look like this. So in our A column, we have time in seconds. So it's actually recorded every 30 seconds for half an hour. We have our control flask that we saw was just air, nothing else in it. Our CO2 flask where we added in our dry ice and the temperatures as it changed over time, it's been recorded here, column C. Column D and column E are the changes in heat for both the control flask and our CO2 enhanced flask. And that change over time is recorded here. What we're going to want to do is just create a graph where we look at these changes in temperatures over time. So we are going to select our column A. You can hold down, depending on your computer, you can either hold down the command key or the shift key to select columns that aren't next to each other. I'm going to hold down the command key and then select D, column D, and then select column E. I'm going to release my command key, and now these three columns are selected. So I can just do that again, where I select column A. You can hold down the command or shift key and select column D and E, because we want to look at the change in temperatures in our control flask and our CO2 enhanced flask over time. I'm going to release my command key. We can go up to the top of our toolbar, right next to our Home tab. We can select our Insert tab. And near the middle, we have our recommended charts. Right next to it, we can select this XY scatter option. And the very first option is for just a regular scatter plot. We can select that, and that would give us our data, our chart. Did anyone want me to go over that again? Okay, awesome. So now in our blue dots on the bottom, this is our change in control. Our orange dots at the top is our change in CO2. We already see that there's over time, there's this difference where almost immediately within this half an hour, the CO2 enhanced flask is going to hold in heat really well and get warmer. But now for our graph, we can add in our X and Y axes titles. So when your graph is selected, you can go to the Add Chart element off to the left side of your toolbar. And on this drop-down menu, you can hover over axes titles. And we can first add in our primary horizontal axes titles, our X-axis, for our time. So once that shows up on our graph, we can just change that to time measured in seconds. Make sure to put in your units so whoever's looking at your graph knows what we're measuring and how we're measuring it. And after we added in our X-axis titles, we can add in our vertical axis title. So we can select Add Chart Element again off to the left side of our toolbar, hover over axes titles, and right underneath primary horizontal, we can select primary vertical for our Y-axis. And this is going to be our change in temperature over time. So when that shows up on our graph, we can just change that title to change in temperature. And that is in degrees C, degrees Celsius. So you would add your descriptive chart title that describes what are we looking at in this chart. But that's basically that one section or what we're making for the one Excel graph for our lab today. And right, so already see this big difference between the two, the CO2 enhanced flask and our regular control. Now we can answer the first part of our data sheet. So we can find that data sheet. Oh, well, did anyone have any questions about any part of this Excel graph?
I have a question.
Sorry.
Yeah, sure.
So I selected A, D, and E, but for some reason my chart only has the blue part.
Okay.
Am I missing something for how you got that like orangish?
Right. I would say, and like D and E, they're both selected for your chart too. Okay. Can you share your screen so I can see?
Yeah, sure.
Yeah. Okay. Can you just we can leave that chart as is right now, but can you select column A, D, and E, and then let's just go back and let's just make a new chart. Yeah. And then can you go under insert and on XY scatter, one of the buttons a little bit to the right, where it looks like dots, right underneath that, like 2 down and 1 to the right. Yeah. And click on that very first option for XY scatter. Yeah, there you go. Great.
Okay, thank you.
Yeah, of course, no problem. Did someone else have a question about
I just had a quick question. How did you change the names of in the legend?
so when you select, let me share my screen again. So say we didn't have this title. Let's just delete that. And let's just delete this. When you add in your XY axis titles, you're going to go under add chart element, hover over axis title, and say if we want to add in our our primary horizontal, you would just click and select that axis title, those 2 words, and then you can just retype it in and say time in S.
What about where it says change in control C and change in
Okay. You don't have to change that. It would be nice to keep that there so we know what we're looking at in our chart.
For mine it just says series 1 and series 2.
Oh, okay. Then I think you can select, and then on your drop-down menu, you can format legend. And I think it might be different for some of the other options, but I need to relook at where to do this. Yeah. Did you also select the top change in control and change in CO2, these 2 labels on top of your D and E column?
I might not have. Let me try to make the graph again.
Yeah. Try doing that. I think then it should change like these 2 titles or the legend at the bottom here. I guess while you're doing that, did anyone else have any questions about?
Yeah, Maggie. I was also struggling to make the chart because when I select A, D, and E, it makes like my chart just doesn't look anything like that.
Okay, can you share your screen so I can see? Yeah.
Okay, can you see that?
I can, yeah.
Okay, cool. So I do A, D, E, and then I go to,
Yeah, perfect.
oh yeah.
And then, yeah.
Oh shoot, okay. It wasn't doing that before.
That's totally okay. I'm glad it worked out. Yeah. Okay. Did anyone else have any other questions? Okay. Okay, awesome. So, right. So, well, now we can answer our Lab 9 Word doc questions. So if we go back to our Lab 9 Canvas page, we can find that our Lab 9 questions right underneath that lab video. So if you click and select Lab 9 questions and assignment, you can also download it here. The Word doc, when it pops up, is going to look like this. And let me make this a little bit bigger. So for our very first question, we created that scatter plot. So that first question is done. You would just submit that Excel file onto Canvas when you submit your responses to these questions. For question 2, write a brief summary of the results of your experiment. So that's referring to that lab video where we had those 2 different flasks, one with air, one with CO2, and we shined a light on it. You would talk about that process and then the difference in temperatures over time for that. For question 3, in your own words, describe how the greenhouse effect works. So considering heat and light that shines in to on Earth and how it's trapped within our atmosphere, and you can talk about greenhouse gases. You could compare it to what an actual greenhouse looks like, but this is just a couple of sentences in your own words on how the greenhouse effect. And then for question 4, greenhouse gases are able to absorb infrared heat energy. So what allows them to do this? You can, this is referring to the molecular structure of greenhouse gases. They're not symmetrical, and so they hold in heat really well. So another couple sentences for that. And then for question 5, compare and contrast the model of the greenhouse effect that was created in lab to that of the greenhouse effect, to Earth's greenhouse effect. So our lab demonstration video, it's a very controlled setup of we just had water with air and then water with our CO2 or dry ice. And so in our on Earth, there are a lot of other types of greenhouse gases too that make a difference. And it's not only CO2, carbon dioxide, but there's other greenhouse gases like methane or water vapor. And so our greenhouse effect or our greenhouse model in lab is a very simplified version of that. And you can just talk about the differences between both of those and how would the Earth's look different from the model's one. Now, if we scroll down, we can look at more recent CO2 data. So this is the website that would go to take us to look at Mauna Loa Observatory collected CO2 data. And we're going to look at today's concentration of CO2 in the atmosphere versus the CO2 concentration in the year that you were born. And then you would just compare those two and look at the increases or differences between those. So when you click on this link, it would take us to this website. Let me share this again. And when it loads for us, this is an overview of global CO2 levels over time. Can you guys see this screen right now?
Yes.
Okay, awesome. Thank you. Okay, so it's recorded CO2 levels over time, and we have our CO2 concentrations in ppms, parts per million on our Y, and time on our X. To zoom in, we can just click and select the times that we want to look at, and then it zooms in for us to these times. So say if we wanted to look from 1990 to more recently, like just yesterday, you can just scroll along this graph, and you can zoom in as closely as much as you need to get to the exact dates. But say if we wanted to look at more recent data from yesterday, we have April 27, 2021, our CO2 concentrations in ppm is 419.49. So that is the most current amount of CO2 for us this year. And we can see that it ranges throughout time, but generally it is rising. And if you want to look at the overview again, you can click on Reset Zoom, this button in the top right, and it would give us the overview level or the overview of the entire graph again, and we can zoom in, and you can also select the year, like the year that you were born, and look at the CO2 concentrations then. So you would try to, because if we look at recent data, as in from yesterday, there's this these rises and like the increases and decreases over time in CO2. Right now, we're looking at one of the highest, like the top of our curve of this one range. So in the year that you were born, you would try to get like that to as close as that like high increase here, the highest point of your range within your birth year. And those are the two numbers that you would record, and you would compare those differences there. Did anyone have any questions about how to use this website? Okay, awesome. So now if we go back to our Word doc, that's how you can answer question 6. So get those two numbers, the CO2 concentration in your birth year, in that range as close as possible to the range that we see on the curve of our current CO2 levels. And now we're going to do some brief calculations where we're looking at the concentrations of CO2 over time. So for question 7, in 1960, the concentration of CO2 in Earth's atmosphere was at 32 parts per million. In 2010, the atmospheric CO2 concentrations were measured at 390 parts per million. Calculate the average annual increase in CO2 between 1960 and 2010. Show your work. I'm going to go over question 7 and question 8 with you all. And if it's easier for you to do this on paper, you can do that and just take a picture of your work and upload it along with your Excel graph and these responses, and I'll just check your work like that. But if you feel comfortable using like the equation tool on like Word doc, either is okay. So you can include your picture here, or you can just type it in. If you were to type it in, you can do something like this. So you're just going to select wherever you want your equation to start, and we're going to go under Insert, next to the Home tab, the Insert tab. And all the way at the end on the right side, we have our equation button. So we can insert an equation by selecting this. And we can start typing our equation there. So first, we know that we're comparing 1990 to 2010, and the concentration in CO2 in 1960 was 320 ppms, and in 2010 it's 390 ppms. So to get our average annual increase, we would just put this in a fraction. To make our fraction function or start our fraction, once you click on the equation, this new toolbar is going to pop up, and that very first, or in the middle, there's this fraction button. If you select that, this very first option of stacked fraction is what we can select to make or start calculating. So we'll just select that, and we're comparing 2010 to 1960 and these two different CO2 concentrations. So at the top, our 2010 concentration of CO2 is 390 ppm. We're going to subtract that from our 1960 concentration of 320 ppm. And at the bottom of our fraction, we would just compare our 2010, or that's the year for our 390 concentration, and we're going to subtract that to 1960. So this is the general setup. This is the starting setup of our how to calculate our average annual increase. We can then hit our equal sign. You can also find other like symbols to put into your equation here in this toolbar at the top. But now we can create another stacked fraction and just say, so 390 minus 320 would be 70 ppm. And 210 minus 1960 is going to be 50 years. And we can just continue and say if you wanted to select the equal sign up here, you would just divide 70 ppm by 50 years, and that would give us, let's just put this in another fraction so we can keep our units. It's going to give us 1.4 ppm over years, 1.4 parts per million per year. So from 1960 to 2010, every year there's 1.4 parts per million of CO2 added. And this is how we can do the calculation for question 7. So for question 8, I'll read the problem to you. So assuming the annual rate of CO2 increase calculated in question 7, so our previous question, it says question 6, but really we're talking about the previous calculation that we just did. So assuming the annual rate of CO2 increase calculated in question 7 stays the same. So assuming that 1.4 ppm stays the same, predict the concentration of atmospheric CO2 in the year 2100. Use 390 ppm in 2010 as your starting point. Show your work. So again, we can just click anywhere underneath our question, and we can start our equation by going under the Insert tab at the top, right next to their Home tab, and all the way at the end of our toolbar, we can select our equation button and just start our equation. So first, since we're looking at 2100 and 2010, and keeping 2010 as our starting point, we're not going to think about any of the CO2 concentrations before 2010. We'll just calculate the difference between the 2 years. So 2100 minus 2010 is going to be 90 years. So the time frame that we're looking at is 90 years. If we're now going to add in and start doing the next part of our calculations, we can just hit enter, and when it takes us to this next line, we'll just go back under Insert and add a new equation. So we know our time frame is 90 years, and we also know that our rate of increase stays the same from question 7, so 1.4 ppm per year. So we'll just retype that in here, and we can do that by clicking on our fraction button in the middle of our toolbar. And that very first option for stacked fraction is how we can retype our rate of increase. So I'll just click on stacked fraction, and we'll just retype 1.4 ppm over year. So we can now multiply our 1.4 ppm by 90 years because that's our time frame, and we can select that multiplication sign in our toolbar at the top. So if your equation tab hasn't been selected, or if it isn't open, you can select it now, and in the middle of our toolbar we can select our multiplication sign, and we're going to multiply this by 90 years. We're going to hit equal to create our equal sign, and just looking at it now, we can see that 90 years, if it's written in a fraction, it would be 90 years over 1. The years, these two units would cancel out, and we would be left with ppm, or parts per million. and that would give us our concentration from 2010 to 2100. So if we would multiply those two numbers, we would get 126.0 ppm. And that is from 2010 from to 2100. This is our CO2 concentrations between these two times. But now that we know that from 2010 to 2100, it's an estimated increase of 126 parts per million of CO2, we can add this to the information that we know in our previous lab or previous question, where before 2010, the atmospheric concentrations was measured at 390 ppms, and we would just add those two numbers together. So we'd start our equation again. So click on the next line and go back under insert. And all the way at the end, we can add our equation and just add the 390 ppm, which is our 2010 atmospheric CO2 concentrations. So we'll add that to our predicted CO2 concentrations after 2010 to 2100, so our 126.0 ppm. And then we'll just add that together, and it is going to give us 516.0 ppm. And this is the estimated CO2 concentrations in 2100. And that is the work that you would have to do for question 8. Did anyone have any questions about how we got these numbers or how to use the equation tool or anything like that? Okay, so in question 9, it's the same process, but our rate or our average annual increase rate, instead of it being 1.4 ppms, it's actually 1.9. And it's the same process, but using a new rate of increase. So that's the 1.9 ppms per year. And then our very last question after you do these calculations is, what do you predict will happen to global temperature of Earth as more CO2 is added to the atmosphere? What are some of the implications of this? So after you've estimated and did some calculations on how much CO2 will be added, what do you think is going to happen in terms of climate change and any additional information outside of what does that mean for people living within the system? That is basically the Word doc with all of the questions that you'll be answering for this lab. Did anyone have any questions about any part of either the Excel sheet or the Word doc?
Yeah, so for number 9, are we just doing the same calculations as 8, but we're plugging in the 1.9 ppm?
Yeah, so you're using 1.9 ppm instead of the 1.4.
Okay, sounds good. Thank you.
Yeah, of course, no problem.
And did you want us to title the Excel chart anything?
Yeah. So you would just put a title that describes what are we looking at. So maybe like CO2 enhanced flask versus control over time, something like that. Yeah.
Okay, thank you.
Yeah, of course. Okay. Did anyone else have any other questions? If not, you can always just stay afterwards and ask me then. But if not, I hope you have a good rest of your week, and I will see you all next week.
Thank you.
Thank you, Maggie.
Thank you.
Have a good day.
You too. Thank you. Hi.
Hi, Maggie. I just want to let you know I was a little late, and I know that the policy says that after 15 minutes it's an unexcused absence. I was just having Wi-Fi issues, so